Welcome to DoveBiology, Bio Lessons to Go. In this video, we will be exploring pH and buffers. So what is pH? Well, in general, we say that pH is going to be a measure of how acidic or basic a solution is. Now, pH is measured on a scale from 0 to 14. We can make this measurement using some sort of indicator. It could be a chemical indicator. When you add the chemical indicator to the solution, it'll change colors, which will indicate a particular pH. Sometimes those indicator chemicals are infused into paper to create pH strips. And then when you dip the pH strip into the solution, the pH strip is going to change color. It's going to indicate a particular pH, whether acid or base. You can also use a pH probe, which is basically an electronic device that's going to measure variations in conductivity in the solution. And then on a screen, it'll do a readout of what the pH of that solution is. Now, one of the things that's kind of new to high school science students is that the pH scale is a logarithmic scale, which means that it's a base 10 scale. For each 1 unit change on the pH scale, we're actually having that correspond with a tenfold change in the acid-base concentration. So for example, if we look on our pH scale, pure water has a pH of about 7. Coffee has a pH of 5. So coffee is actually 100 times more acidic than pure water. When we go from 7 to 6, we are going 10 times more acidic. From 6 to 5, that's 10 more times acidic. So the total change is going to be 100 times more acidic. Each 1 unit change on the pH scale, either towards the acidic or towards the basic, is going to correspond to that tenfold change in acids and base. So when we're talking about an acid, what are we really talking about? Well, in general, an acid is going to be a substance that on the pH scale is going to be below 7. The reason why it's going to show up as below 7 is because what's happening typically when an acid goes into solution, when it's dissolved in water, it's going to release a lot of hydrogen ions. So charged hydrogens, H pluses. And the concentration of those hydrogen ions is what's going to be indicated by our indicator solutions or our pH probes. The more hydrogen ions in solution, the lower the pH. In fact, the pH scale, when we say pH, we're talking about the power of hydrogen. So how many hydrogen ions are in solution? On the other side of that, our basic or alkaline substances are going to typically have a pH above 7. And the reason why they have a pH above 7 is because when a base is put into solution and is dissolved, it produces hydroxyl ions or OH minus ions. And that's going to be indicated by our pH paper or our pH probes as being basic and have that pH above 7. Now, water is kind of unique when it comes to pH. Remember that water, H2O, is one atom of oxygen covalently bonded to 2 atoms of hydrogen. But in this covalent bond, the oxygen doesn't share its electrons equally with the hydrogens. As a result, oxygen takes on a slightly negative charge, while hydrogens have a slightly positive charge, making water a polar molecule because it has slightly opposite charged ends. When water molecules are nearby each other, they can form these weak temporary interactions between each other, called hydrogen bonds, where a slightly positive hydrogen will be attracted to a slightly negative oxygen, as indicated by this dotted line here. But sometimes this interaction can be kind of intense, and a water molecule might actually pull a hydrogen ion away from its neighboring water molecule. What this creates is what's called a hydronium ion, H3O+. and a hydroxyl ion, OH minus. With the hydronium ion, we kind of can consider that just H's, and then we have the hydroxyl ions are the OH. So with water, at any given moment, especially pure water, you're going to have a balance of H's and OH's because together they would make water molecules. Now, pure water is going to have, with nothing dissolved in it, will have a pH of 7 when we test it with a pH paper or a pH probe. Most of the water that you encounter in your life is not pure water. It's going to have different ions or metals that are going to be dissolved in it. So the water from your tap is not pure water. It's going to have stuff in it. Pure water you can get at the store is called distilled water. It's undergone a process to remove all of the impurities, giving us pure water. And if we tested that, it would have a pH of 7. Now, pH is really important when it comes to biology and living things. pH has to be balanced for an organism to be within homeostasis. Um, Strong acids or strong bases can actually damage tissues. And pH is really important for certain molecules because it allows for those molecules to function. For example, the enzymes in our stomach, like pepsin, that's going to help with the digestion of proteins, it really wants an acidic pH. Whereas salivary amylase, which helps to digest carbohydrates in our mouth, needs to be closer to neutral. It works best around a pH of 6. If these molecules are placed in a pH that's outside of their expected range, it causes them to unravel or denature. And so they don't work anymore. So they need like that optimal pH kind of condition. Now, most of our living systems are going to have some sort of way to maintain homeostasis. And one of the ways that they do that is by using a chemical buffer mechanism. So a buffer is going to help to maintain that optimal pH range for that given area of the living system. For example, the stomach lining is going to have a mucus barrier, which is going to buffer the sensitive stomach lining from the acid that's being produced there. Unfortunately, our esophagus doesn't have this mucus buffer, and if a person has acid reflux, where that acid goes back up into the esophagus, it can cause esophageal erosion. Basically, the acid damaging that lining of the esophagus, and just a temporary acid reflux. You know how that burns because the esophagus is not buffered against that acidic pH. Another good example of a biological buffer in us is going to be the buffers that work in our blood. Now, the way a buffer is going to work chemically is that it combines with either the acid or the base to either take up the additional hydrogen ions or the hydroxyl ions so we can kind of keep that pH at that optimal range. So for blood, the normal blood pH range is between 7.35 and 7.45. Getting just outside of that pH, and if we get down to 7.2, we're in a condition called acidosis. And if we get down to like a pH of 7, it can result in death. So maintaining that balance is really important. Now, our body employs a number of buffer systems in order to regulate our blood's pH. One of the common buffers is bicarbonate. If, for example, you're doing some strenuous activities, one way your blood pH could be impacted is you have an increase in carbon dioxide in your bloodstream. When carbon dioxide dissolves in water, it produces carbonic acid, which donates hydrogen ions into the solution, reducing the pH and making your blood slightly acidic. To respond to that, our body will use our bicarbonate buffer, which will try to regulate that pH. Plus, we are going to try to breathe faster to remove that excess carbon dioxide and bring our blood pH back to its normal state of 7.3 to 7.4. Now, sometimes we overcompensate, and we have to, and our blood gets a little too alkaline. So to compensate for that, we would then have our kidneys kick in, and they would reabsorb some of that bicarbonate to allow the pH to go back down to a normal state. So there's a constant back and forth in our body to try to maintain that blood pH so that it stays optimal, allowing for us to live. So what you guys are going to do today to kind of finish up is you're going to explore pH and our bicarbonate buffer system by doing two virtual labs. The first virtual lab, you're going to go to explorelearning.com and log in with our generic logins, and you're going to test virtually the pH of various common household substances, just to kind of explore that a little bit. And then you'll head over to Google Classroom and you'll be able to download a little interactive presentation that I produced for you, and then explore the role of buffers in maintaining homeostasis by constructing a model of our blood buffer pH system. I hope this video was helpful, and I hope you enjoy the virtual labs, and I'll see you soon.